So here's a quick introduction to the CoCoA system. What we're seeing here is in fact a window from the Emacs browser. On my particular computer it's running under Ubuntu Linux. And what we're seeing here is actually a source file for CoCoA. And we'll see a little bit later on that yellow here corresponds to comments. So this is a quick introduction to CoCoA. Those of you who've already used CoCoA a bit will probably learn nothing new from this system. So CoCoA is an interactive system built on top of a C++ software library, which we call CoCoA-L1a. So if you like, you can think of CoCoA as being an application which uses CoCoA-L1a for doing the mathematical computations inside it. So assuming that you're using the Emacs interface, that's the one that I use mostly. So I find it convenient. I've been using Emacs for many years. There are other possibilities. Anyway, for this demo here, we'll be using Emacs. So here, for example, if we want to start CoCoA, then inside Emacs we can type this sequence here just after where the cursor is flashing. It's a little bit hard to read, so I think if you're using proper Emacs language, you would then say it's meta x CoCoA ret, or ret is return. So meta x in this particular case I can achieve by typing escape x, so I'll press that now, escape x, and you'll notice right at the bottom of the window down here, a little m minus x has appeared because I've typed escape x. Now I can type CoCoA all stuck together like one word, and then I press return or enter. So this has now started CoCoA. It's quite small, so I'll just make it a bit bigger. And switch back to the other window. Actually, I think I'll make this other window big so it's easier to see what's going on. But the window with CoCoA is still there, we just can't see it at the moment. So that's how we can start CoCoA. Oh, and then there's also, once you've got CoCoA started, what do you do to quit it? The easy way, since CoCoA was built in Italy, is to use the command ciao, which can be used for both a greeting when you first meet and also a salutation at the end when you're going away. So that's ciao followed by a semicolon. So the semicolon is important. And if you're inside CoCoA, that will end it. For those of you who are interested, the name CoCoA comes from the expression computations in commutative algebra. Now we can see CoCoA. So that's just a brief explanation where the name comes from. So before we go too much further, as I say, the file that we're looking at here is actually written in the language that CoCoA uses. And so comments explaining what's going on, they appear in yellow, at least with my chosen colors. And there are three ways of making comments in a CoCoA source file. One is a minus minus. That this sequence introduces what's called an end-of-line comment. So the two minuses plus any characters coming after it are regarded by CoCoA as being a comment, and they're effectively ignored. The same applies to slash slash. That does exactly the same. Slightly more complicated is a comment where we have to mark both the start and the end, and that is we have slash star. So that marks the start of a comment, and then star slash marks the end of it. So those of you who know the programming language C or C++ are probably aware of at least the second and third ways of making comments. I use whatever's convenient. I don't use slash star and star slash much myself. I tend to use end-of-line comments. As we can see here, an end-of-line comment can in fact apply to the entire line. So as far as CoCoA is concerned, the line where the flashing cursor is really just an empty line. It simply sees it that there's nothing followed by a comment, and the comment is ignored, so it's effectively an empty line. So, a little bit of preamble, let's get on with something. So, CoCoA has a built-in online manual, and we can search for entries in it using a question mark. So, for example, if I put the cursor on this line, question mark gêné would look up in the manual for entries related to gêné. So I think here, if I go up to the top of my Emacs window under CoCoA-5, the first entry here is send line to CoCoA-5. And so what I want to do is send the line where the cursor is to CoCoA-5 to see what it does when it receives question mark gêné. I can also do Control-C return if I want. That would achieve the same thing. So let's do that. And so Emacs has now split the screen into two parts. In this particular case, the lower part is what we were seeing before, the input, and the upper part is how CoCoA reacted. So if you remember, we started CoCoA before. So if I go up to the top here, we can see the start that we had before. Then where the cursor is now, we can see the question mark gêné was sent over to CoCoA, and then we see here what CoCoA's response was. And so this is the online help entry for gêné. Yes, we can ignore this first thing here. It's a reminder to me to correct something in the manual. So there isn't actually an entry called gêné, but there is one called gêné basis. And then this tells us a bit about it. So it's a function which expects one argument, which is an ideal, and it returns a list of ring elements. And then so, the line here, this is giving us, if you like, the signature of the function, what it expects as arguments and what it returns as a type of value. This is then followed by a verbal description of what it does. In this case, it's very short. So this function returns a gêné basis of the ideal I. So this I refers to here. And as a comment, the code here was originally written by Mario Albert. He was a PhD student in Kassel. Here's an example of how it could be used. We'll see a bit later on what's going on here. So we're using the ring Q, X, Y, Z. So we have rational coefficients and variables, or indeterminates we call them, X, Y, and Z. Here are a list of 3 polynomials. They're going to be the generators of our ideal. And then we use the command gêné basis of the ideal generated by this list. And here's the answer. That's the end of the example. We also see search keys. So this entry here we could have found if we looked up gêné or basis, or maybe also the author Mario Albert. It suggests that we also look at an entry G basis. That's the short name for calculating a Grosvenor basis. And then here we finally have the end of the gêné basis entry. So this one's nice and small, and it fits conveniently into my screen here. Some entries are much longer. So let's go back to the input. So what do we have here? So here we had single mark gêné, and that gives me the entry relating to a gêné basis. So a double question mark lists the titles of manual pages which contain the keyword that you searched for. So in fact, CoCoA does have a factor command, but if I do double question mark factor and send that, then we see that CoCoA up here simply lists all entries that match factor, and so we see there are quite a few. There is the factor command by itself, but there are also plenty of others. Some of them, so for example, fixed divisor does not the name does not involve the substring factor at all. But if we look up at the entry, we would then see it's probably a keyword. Similarly, is divisible, you could think of as being is a factor of, and so once again that appears as a keyword here. Also notice that these searches here are case insensitive, so sometimes factor appears with a capital F. Here it's all lowercase, here it's inside a word and all lowercase, and so on. Factorial. So it ignores case here. So there are essentially two ways of using the manual. A single question mark tries to look for a single entry matching the keyword that you look for. Double question mark then lists the titles of manual pages which contain the keyword that you're looking for. One last comment here. If we ask for tutorials, so there are some tutorials in the manual. We'll see that there are, oops, pressed the wrong thing here. So it says there's no exact match for tutorial. Have we got, so if there had been an exact match, then we would have seen that page because we asked for just a single question mark. Since there was no exact match, it then effectively reverts to the behavior of the double question mark. So these are all 14 matches for the string tutorial. And then we see there are several tutorials here. There's a basic tutorial and then tutorials about specific aspects of CoCoA. And so you can choose which one you want. You'll notice that these are printed out as a question mark followed by some string. This is done in such a way that you can, in principle, copy what is here and then give that as input to CoCoA, and it would then give you the corresponding manual entry. So that's all I wanted to say about the online manual. I hope you will find the time to have a look at least at some of these tutorials, especially the ones that you think are of most interest to you. So if you are going to use the Emacs interface, which is the one that I use most and also Annie Bugatti uses most, so it's the one that's best developed perhaps, but there are other possibilities. It's probably worth looking at this entry, for example. Some of these are quite basic. The ones about variables and assignment are, of course, quite basic. Some are more advanced. The ones about homomorphism, for example, are more advanced. Anyway, take a bit of time to look at that. So let's proceed with this quick introduction. So I'm just going to show a few aspects of CoCoA. So the first aspect I want to look at are lists. List is here is somewhat like vectors or arrays in C or C++. So they're a bit more flexible. So it's a flexible data structure, but the entries in a list are indexed with indices starting at 1. So that's an important point. For example, C and C++ have indices starting at 0. Moreover, the entries in a list, different entries can be of different types. They're not required all to be of the same type. So it's quite a flexible data structure. If we print out a list, then it's printed out as sequences of values separated by commas inside square brackets. So here's a simple example. You can create a list of consecutive integers. This uses the dot operator. So let's send that to CoCoA, and we'll see that indeed it prints it calculates and prints out the list 3, 4, 5, 6. We have some other constructors a little bit more sophisticated, where we use the vertical bar to mean where or perhaps such that. So for example, in this line here we would have, so we can regard square brackets as saying the list of n in the range 10 to 20 such that is prime of n. Send that to CoCoA. And yes, although given the answer here after the comment, CoCoA has actually calculated it. So this is the value we expect. Here, this is the list of n squared, where n is in the range 1 to 10, or in fact n is in the list from 1 up to 10, and n satisfies is prime. This is a little more complicated, but I hope you find it relatively easy to read and understand. So again, we can get CoCoA to calculate it. Another feature in CoCoA is this it variable. It's a variable that we can't actually assign to directly ourselves, but if we calculate a result, like we have done just here, this result was a list, we calculated a result but didn't assign it to anything, then CoCoA automatically puts it into the variable it. This means that if we calculate something and then want to then realize we wanted to use that for something further, we can then refer to the value using it and then, for example, put it into a named variable. So we can work on it further. So for example here, L, so we assign to L the value of it, and that means that L now contains the list that we had here. And then once we got a list, so in this case I've chosen L to be mnemonic, it contains a list value, I can then access each individual entry in the list just by putting the index in square brackets after it. So L square brackets 3 is the third element in this list here. So index 1, 2, 3, 4. Third element is 25. So L of 3 will give me 25. So if you want to find out things related to list, you can look it up in the manual. There are quite a lot. If I do this, we'll see here that it just a bit too many to fit in my Emacs window here. So lists, oops. Right. Lists are a convenient data structure and they're quite flexible. And we'll use them essentially without further discussion later on. Now something more mathematical. I'm assuming you already know the mathematics. You have an idea of at least what commutative rings are, or polynomial rings, and ideals. We're not going to cover the mathematics of those. This is how we can deal with them in CoCoA. So if we want to compute with such things in CoCoA, the very first thing we have to do is we have to create and state which ring we want to compute in. So this particular line here, this is assigning to the variable p the polynomial ring with coefficients in the rational numbers. So QQ refers to the rational numbers, and with indeterminates x, y, and z. So x, y, and z are new indeterminates. So we're specifying those indeterminates here, and we know that because we have this slightly funny assignment here. It's not a normal colon equals, it's a double colon equals. That then tells CoCoA that what's appearing on the right is the specification of a ring. So it'll be the coefficient ring, square bracket, and then a list of the indeterminates that we want to use. So we'll assign that. So P now contains this polynomial ring. Yes, and something that we don't see here will become important later on. Polynomial rings have associated with them something called a term ordering. In this particular case, since we didn't say anything special about it, it chooses by default something known as the degree reverse lexicographic ordering, which happens to work well for Grosvenor bases. So we've created this ring, we put it inside a variable p. We still have to tell CoCoA that we actually want to manipulate polynomials inside this polynomial ring p. So we do that using the use command. So we're now telling CoCoA we want to use p. We can do that. This then means that the indeterminates of the polynomial ring, that is x, y, and z, are now accessible just by typing their names. So for example, I can then type in this polynomial here. F is then the square of 2 times x plus 3 times y plus 4, and it works the way we expect. If I try to type that in without saying use p, it won't work because we haven't yet told it which ring we want to use, and so we don't have these convenient shortcuts for the indeterminates. So that's typed in the polynomial. You can also tell CoCoA to print out the polynomial usual way to do this is the print function, or println. Println prints the value out and then puts a new line afterwards. So here it is, and we notice that CoCoA has already, in some sense, simplified the polynomial, or expanded it out into a sum of terms, and it always does that. So in fact here, if we look at the lower part, where the cursor is, I have two cursors. So as far as CoCoA is concerned, a polynomial is a list of monomials, a monomial being a coefficient and a power product. And this list represents their sum. And the power products are in decreasing order, according to the term ordering that we used. So that means that every polynomial in a particular ring has a unique representation. So it was just a quick way of how we could create a polynomial ring and a value in it, and we can print it out. Once we got that, of course, we can do normal arithmetic operations with them. We can add, subtract, multiply, divide if that's possible. Division will work only if it's an exact division, otherwise you get an error. Other things that might be useful are inspector functions. They allow us to look inside the structure, in this case of a polynomial, since we're dealing with polynomials. So I've got a polynomial, I put it in F, so I can ask the polynomial, to which ring do you belong? And this is what CoCoA replies. It doesn't reply P, which might surprise you a little bit, but remember P is simply a variable, and it contains some value. So I could also assign the values in P to some other variable. So the variable name is somehow independent of the ring. So here, CoCoA has tried to print out a description of the ring that doesn't depend on the variable that's involved. So it's a ring with identifier 3, and then it prints out a description of the ring in a string in a convenient way. So this is indeed what we expected. Now it's also possible to create other rings that look essentially the same, but they will have different IDs, and they might, for example, have different term orderings. So when you print out a ring, it prints out the ID, and that tells us, so two rings that have different IDs are different as far as CoCoA is concerned. Even if every other aspect of the ring is the same, if the IDs are different, then CoCoA regards them as being different rings. So let's go on. So we can find out, given a polynomial, we can find out the ring it belongs to. We can ask how many terms it contains. So in this case it's 6, but we can count them. So here's the first term, second term, third, fourth, fifth and sixth. So yes, there are 6 terms here. Since we have a well-defined ordering on the terms, we also have something known as the leading coefficient. So that's the very first coefficient. We can see it there, it's 4, and the LC function gets that. LPP gives me the leading power product, so that's the part of the leading monomial, but without the coefficient. So the coefficient is simply forced to be 1, so that gives me an x squared. Some people also call that the leading term. That also works in CoCoA, but at least here we're using leading power product, as it's slightly more monomial. So leading, slightly more mnemonic. Leading monomial gives me the leading monomial as we see it here. So it's both the coefficient and the power product multiplied together. So leading power product and the leading monomial are in fact themselves polynomials. So they're polynomials in this same ring. The leading coefficient is an element of the coefficient ring of the polynomial ring here. So LCF here, 4 is actually an element of the ring Q, the ring of rational or field of rational numbers. We can do further inspection into polynomials, pull it apart, rather than getting just a leading power product and so on. We can ask for the support, and that gives me a list of all power products in decreasing order. So we can see that from here. So we get x squared, x times y, y squared, x, y, and then this one has a 1. Of course, we don't normally write 1. We should actually think of as being x to the power 0 times y to the power 0. And so here we see all the power products that appear in F, and then coefficients gives me the list of corresponding coefficients. So we print that out, and then we will see that the coefficients here are in exactly the same order as we get them here. So we can either use LC and LPP just to get effectively the first elements of these lists, or if we want in a program, we can also get all the power products in the support and all the coefficients in one go, in 2 separate lists, and then we can index into those lists if we want. So this is one way where we can get in, pull a polynomial apart into its various components. So let's proceed. So that was how we could peer inside a polynomial. We can also have inspector functions for rings. So we're hoping that the names of the functions are helping you to guess what they do. So I defined earlier on the polynomial ring P, so it's Q of x, y, z. So we can ask, is that ring a polynomial ring? So the answer is yes, but CoCoA returns a Boolean, so the answer is going to be either true or false. So is poly a ring? And the answer is true. So yes, it is. We can also ask for the coefficient ring of P. So in that case, it's QQ. Yes, you might then wonder why didn't that print it out as ring with ID? I guess it must be a special case. We can ask how many indeterminates, so the number of indeterminates in the polynomial ring P, 3, and we can also ask for index of P. So this actually gives me a list of polynomials, each polynomial being in P. And the first polynomial has value 1 times x to the power, 1 times x to the power 1. Next one is 1 times y to the power 1, and the last one is 1 times z to the power 1. So those are polynomials. So given a polynomial ring, we can get some information out of it. Ideals. One of the raison d'etre for CoCoA is to be able to calculate with ideals in these commutative polynomial rings. So in this particular example, we're going to create an ideal, and then having created the ideal, we can then create a quotient ring. Since I've not told CoCoA to use any other ring, so it will keep using the ring P until I tell it to use another one. So that's still the current ring in CoCoA, and that means that I can use the names of its indeterminates conveniently just by writing them down. So here, for example, the line that the cursor's on, I can send that to CoCoA. So we're going to assign to the variable I the result of this function ideal with 3 arguments, which are 3 polynomials. So 2 of the polynomials are given explicitly here, and the third one is f. That was a variable we had before. We stored a polynomial into that variable. And so this has created the ideal generated by these 3 polynomials, and that's going to be an ideal inside the ring P. CoCoA's, as I say, one of its raison d'etre is to be able to calculate with ideals, in particular to calculate Grosvenor bases. So we can calculate a reduced, we call it G basis. To avoid names that are too long, sometimes we use abbreviations. So G basis is short for Grosvenor basis, or reduced G basis is short for reduced Grosvenor basis. So we can calculate that. And here's the result. It's a list of polynomials. So first 2 here are actually 2 of the generators, and then we have 2 other polynomials here. And here we can see that the coefficients are, at least in some cases, rational numbers. It's a reduced basis, so that all the polynomials are monic. That is, the leading coefficient of each of these polynomials is going to be 1. That's one of the characteristics of a reduced Grosvenor basis. Possibly a little bit hard to read it like this. Luckily my Emacs is wide enough that it all fits onto one line. But in other cases, the reduced Grosvenor basis may be a bit bigger, or indeed we may have any list that's a bit long and hard to read. So the indent function lets us read lists a bit more easily. So if we tell it to indent the previous value, so I calculated this reduced Grosvenor basis, didn't assign it, so that's automatically the value of the it variable. I can then tell it to indent that, and this simply prints it out in an easier to read way. So here it is, we have one entry per line. That's just to make it easier to read. So we have an ideal, we've printed out its Grosvenor basis. We can also do further things. So I could calculate the quotient ring. Let me just comment here that here we have normal assignment. We don't use this double colon equals because on the right hand side we're not introducing new indeterminates. So we don't have on the right hand side something of the form, say, coefficient ring, open square brackets, new indeterminates, close square brackets. So we need colon colon equals only if we're introducing new indeterminates on the right hand side. Otherwise we just do normal assignment. So this has calculated the quotient ring, but the current ring is still P. We can tell CoCoA now to use quat ring as the current ring. So this now means that the indeterminates in quat ring are accessible. So for example, we can type in 10x squared plus 28x plus 25, but x here is now interpreted as an element in the quotient ring. And indeed, so the input was 10x squared plus 28x plus 25. CoCoA automatically reduces that to a normal form inside the quotient ring. And so the value we get is equivalent in the quotient ring to what we gave as input, but it's clearly different from what we typed in. So it's been reduced to a normal form. So in this particular case, we can see that in fact this polynomial is nilpotent. If I calculate its square, I actually get 0 as the answer. Well, I get 0 inside brackets. Those extra brackets are there to remind me that I'm not working with as it were, a normal 0, but I'm working in a quotient ring. So that's just what I wanted to comment in a quick introduction to rings there and ideals. Ring homomorphisms. So we've tried to make ring homomorphisms relatively easy to use. So in CoCoA, ring homomorphisms are useful for two things. They can be useful for moving a value from one ring to another, and so in more general situations, ring homomorphisms can also transform the value at the same time. So the simple applications when we would use a ring homomorphism to move a value from one ring to another, but we can do more general homomorphisms. So we're going to continue with the polynomial f that we had before, which is in the polynomial ring P. Now we're going to make a new polynomial ring that looks much like P, but instead of having degree reverse lexicographic ordering, or degrevlex as we call it for short, we're going to have one with lexicographic ordering. We do that, so this is more or less the same as what I did before when I defined the ring P. So we have the double colon equals here, because on the right hand side I'm now going to specify coefficient ring, square brackets, the indeterminates. These have the same names as before, and then I've got this extra comma lex afterwards. So this is a comma lex is how I can tell CoCoA I want to use a different term ordering. So in this particular case, lex is short for lexicographic. So p-lex is now a variable whose value is this ring, a polynomial ring with indeterminates x, y, and z, and lexicographic ordering. I can ask for a list of its indeterminates. We've already seen that before for the ring P. And here we have something that's possibly a little bit surprising. So we can print out the indeterminates of P and those of p-lex, And we'll see that when they're printed out, they look the same, but they're not equal. So let's do that. So the indeterminates of the original degrev lex ring, P, if we ask for the indeterminates, we get that. If we ask for the indeterminates of the lex ring, which we've just done before, we get an answer that's apparently the same. But they're not the same. If I were to try to ask CoCoA if they're the same, it would actually give an error saying that they're elements of different rings. So even though mathematically you could say both rings are the same, it's Q of x, y, z, as far as CoCoA is concerned, they're different. One has a lexicographic ordering, and the other one has a degrev lex ordering. Let's see how we can now use a ring hom to move from P to P lex. So we're going. So this line here, where the cursor is, right-hand side is defining a polyalgebra hom, going from the polynomial ring P to the polynomial ring Px, and the indeterminates in P, the first indeterminate in P, is going to be mapped to the first element in this list here. The second indeterminate here will be mapped to the second element of this list, and so on. Having done that, we then save the result in the variable map to lex. We've done that. Let's have a quick look, see what map to lex looks like when we print it out. Oh, this is actually a bit too long for my window. So, this is a little bit hard to read. So it's a ring homomorphism. Okay, we've got that so far. Then it says what the domain is and then what the codomain is. So it's from Q of xyz to Q of xyz. But notice here that the IDs are different. So as far as CoCoA is concerned, these two rings are different. We know, in fact, that this first ring has term ordering degrev lex, and this second ring has term ordering lex. Then it summarizes how the indeterminates of the domain are mapped to elements of the second domain. Now, in this case, it's quite simple. We're mapping x to x, y to y, and z to z, which is what we want if we want to try moving a polynomial without actually transforming it. So here's the polynomial f that we had before. If I apply map to lex to it, I get the same polynomial out because we're mapping x to x, y to y, and z to z. However, in the first case, this is an element of P, and so its terms are ordered by degrev lex. In the second case, they're ordered by lex. In fact, the first two terms are in the same order. But then we see that the other terms, as we go further on, these two have essentially swapped order. Sorry about the flashing. So in this case, the terms are decreasing order according to lex. These are decreasing order according to degrev lex. So we can see that these two polynomials are clearly equal, even though the terms have come out in a different order. If we ask CoCoA, are they equal, it gives an error. So the first error here is error, values are in different rings. So what CoCoA actually says is error. Elements must be in the same ring. Mixed ring operations are forbidden. And then the error actually came from CoCoA-Lib, that's doing the work underneath, when trying to compare two ring elements to see if they're equal. And then finally here is where it was in CoCoA 5. So while trying to do this equality test here between it and f, that's where the trouble came up. Which, of course, we knew that anyway. We were expecting it. At least I was expecting it. I've been mentioning about inspector functions for ring hom. We can ask what the domain is, and we can ask what the codomain is. So these two cases, nothing too surprising happens here. The domain is P, and the codomain is P lex. Proceed a little bit further on. Matrices is the last part for this video, or this screencast. So CoCoA can do some sort of simple operations on matrices. If you want to find out all possible operations, then you can search the manual for !mat. And that will give you everything where mat appears as a keyword, and you'll also see that one of them is, well, let's just do it. So it's probably quite a lot. And then we see here at the end commands and functions for mat and commands and functions returning mat. So here format means operating on matrices. Whereas, and these are other ones that may not have matrices as arguments, but the result is going to be a matrix. Anyway, so here are a couple of ways of creating a matrix. So first one, matrix M. So M is just a variable, again with a mnemonic name, and it's matrix. And then inside we have a list of lists. So it's a list of rows. So the first row of this matrix is 1, 2. The second row is 3, 4. And since we didn't say anything particular, by default, the entries are rational numbers. I can also put in as a first argument the ring that I want the entries to be in. So here's a second variable called m_zz. It's essentially the same matrix, but I've now said explicitly that I want its entries to be regarded as elements of the ring of integers. When we print out a matrix, it tries to print it out in a reasonably easy to read way. And here it is quite explicit about the ring which contains the entries. So we see that immediately. We can also do arithmetic with matrices in a fairly natural way. So here, for example, m squared minus 5 times m gives me this matrix. Once again, we have some well, I suppose the only inspector function we have is ring of m, so that tells me the ring to which its entries belong. Then we have other functions, for example, determinant. We can calculate its inverse. Notice that if we tried to calculate the inverse of mzz, that's not going to work. Let's just do that. So this, because the oops, it should be an underscore. Because the inverse is not a matrix of integer entries. So it tries to invert a matrix in the same with entries in the same ring, and this should give some error. Yes, so we get an error, inexact division. Somewhere it needed to do a division which produced a non-integer result. So CoCoA-Lib reported that when trying to divide two integers, and CoCoA-5 says that this occurred while trying to do inverse of mzz, which is what we expected. Just a quick comment here about, fairly easy, if you are doing arithmetic between matrices, be a little bit careful about the order. So let's define 4 matrices here. 2 of them are row matrices, 2 of them are column matrices. They're relatively big. They have more than 1,000 elements in them. So matrix multiplication is associative, but if I bracket them in 2 different ways, the time of computation can vary considerably. So if I do it this way, it's essentially instant. If I bracket things this way, it's quite a bit slower. And CoCoA doesn't try to be clever. It just it does what you tell it. It doesn't try to look at the expression and say, "Oh, I can get that answer faster." So a quick exercise: why was one way much faster than the other one? So we come to the end of what I was going to say here. I'll produce 2 more short videos. One will be about defining new functions in CoCoA-5, and then there'll be a longer, more detailed example, which will be in a separate file. So one will be about a function for calculating elements of the Fibonacci sequence, and the other one will be about Euclid's algorithm for calculating GCDs.